Hi, everybody. Welcome back. Today we're going to start to go over Chapter 8, which is focused on rotational motion. Chapter 8, there's actually a lot jammed into that chapter. So I'm going to break it up into a couple shorter lectures. So let me share my screen. So Chapter 8 is focused on rotational motion. Okay. And there's several aspects to rotational motion that we're going to discuss. This lecture is going to focus on just simply describing rotational motion. Okay? We're just going to talk about, how fast is this thing rotating? How many revolutions does it go through in a given amount of time? Is its rotation accelerating or decelerating? Okay. That is what we're going to focus on today, simply describing rotational motion. Okay. And then in the next lecture, we're going to talk about why objects rotate the way they do, and another principle of conservation of angular momentum. Okay. So, and this is very similar to the way that we have been treating linear motion, right? When an object moves in a line, right, we first described it using kinematics equations. And then we talked about, well, what causes the object to move the way it does? Well, it needs a net force on it to get it to accelerate. Okay. Same thing happens with rotational motion. We're going to talk about rotational kinematics. Okay, so we're just going to describe the motion using our kinematics equations for rotational motion. And then we will discuss later on what causes the object to rotate the way it does. And rotational motion has so many applications in our everyday lives, as you can see here. Just simply the Earth rotating about its own axis. Rotating blades of a helicopter, a Ferris wheel. When we drive our car, right, the wheels rotate a certain amount. Merry-go-rounds at the park, right? And if you've ever been on a merry-go-round, and if you've ever experienced this where you start on the edge of the merry-go-round and you work your way into the center, what happens to the merry-go-round? It starts to speed up faster and faster and faster, right? We're going to be able to explain why that happens using physics principles. But first, let's just get the basics down for rotational motion and describing rotational motion. So the first thing we need to discuss when talking about rotational motion, how much an object rotates by, is rotational distance. This is the quantity for measuring how far an object has rotated, and that's an angle. So when we talked about linear motion, we just said, hey, the object moved 10 meters. That was the distance that the object moved, right? Well, here, when we talk about rotation, we're going to say, how much did the object rotate? How much of an angle did it rotate through? And we usually use revolutions, radians, or degrees as our angle. And the symbol that we will use for rotational distance is this called theta. And just as a reminder, in case you've forgotten a little bit about the difference between revolutions, radians, and degrees, let's just remind ourselves. In a circle, it's a terrible circle, but just bear with me. If you go around all the way around the circle, you've gone through one revolution. One revolution in degrees is 360 degrees all the way around. And in radians, which is a ratio of the arc length divided by the radius, this would be 2 pi radians. So if I'm describing the object's motion and I observe this thing in 1 minute, it goes around 10 times, we would say that it has 10 revolutions per minute. So it's gone through 10 revolutions. That's the rotational distance that the object rotates through. And when we learned about linear motion, right, the next step was talking about the object's velocity, right? How far does it go in a given period of time? We can do the same thing for rotation. Rotational velocity is how fast an object is rotating in a given period of time. The units for that is going to be the rotational distance divided by a time. So it could be radians per second as one unit for that. Revolutions per minute is another very common unit of rotational velocity. You could even say degrees per second. In this class, we'll mostly stick with radians per second. And the symbol for rotational velocity is this funny looking W. It's called an omega. We've ran out of letters, now we're going to use Greek letters. So this tells me how fast is an object rotating in a given period of time. Through how many radians does this thing rotate in 1 second, for example? And you guessed it, we can also talk about an object's rotational acceleration. When an object moves in a circle, or when an object is rotating, or if it's moving in a circle, it's possible that the object could be speeding up or slowing down in this circular path, right? In this animation, on the left-hand side, the object is rotating at a constant rate, right? Do you see that it goes around the circle and it's neither speeding up nor slowing down in the circle. It's just going at a constant speed in a circle. So we would say it has constant speed, it has constant angular or rotational velocity, omega, and it's not accelerating in its rotation, right? So its rotational acceleration would be 0 for this left-hand side. Rotational acceleration is 0 for this case. But if I look at the animation on the right-hand side, it's showing increasing speed. So in this case, the rotational velocity is not constant. It increases and then it decreases. So non-constant rotational velocity. It's slowing down here. And then it begins to speed up, right? So the rotational velocity is not constant here. And that means that the rotational acceleration is non-zero. Non-zero. It does have a rotational acceleration here. It's either speeding up or slowing down. Rotational acceleration is the rate of change in the object's rotational velocity. Change in rotational velocity over change in time. And so the units for that could be radians per second every second, or radians per second squared, revolutions per second squared, something like that. And the symbol that we will use for rotational acceleration is this funny looking A or alpha? Okay, so I know there's a lot on here, but you don't have to write all of it down, okay? Because the left-hand side is already stuff that you know. The wonderful thing about rotational motion is that we can make an analogy between rotational motion and linear motion that we've already learned. Because so far we said, hey, in linear motion, the object moves a distance d. In rotational motion, the object moves a rotational distance theta. That's the analogy here. Average velocity is the change in position over the change in time. Average rotational velocity is going to be the change in rotational position over time. And when we learned about linear motion, the acceleration is the change in velocity over the change in time. Rotational acceleration is the change in rotational velocity over time. So everything in linear motion has analogy in rotational motion. And you might guess that the kinematics equations that we used for linear motion, v final equals v initial plus at, and distance equals the initial velocity times time plus 1/2 at squared, we can write those in rotational motion as well. Do you see v velocity, its rotational counterpart is rotational velocity omega. Initial velocity is the initial rotational velocity. Acceleration, angular acceleration, and t for time. So there's a direct translation. And then for linear motion, distance, the rotational analog is rotational distance, theta. How many radians does this thing rotate through? And then we have the same translation for the right-hand side as well. So these are like our kinematics equations for rotational motion. So isn't that nice? So even though it looks a lot different, we're using a lot of different symbols, we're using some different words to describe it, there's a direct translation between linear motion and rotational motion. So let's practice this. Let's suppose we have a merry-go-round. It's accelerated at a constant rate of 0.005 revolutions per second squared starting from rest. What is its rotational velocity at the end of 1 minute? And how many revolutions does it go through in this time? So let's write down what we're given. We know that it's rotating at a constant acceleration, rotational acceleration of 0.005 revolutions per second squared. And it also says it starts from rest. So its initial rotational velocity is 0 revolutions per second. We want to know its final rotational velocity after a time period of 1 minute. Let's convert 1 minute to seconds since we're in revolutions per second squared. So 1 minute is 60 seconds. So we can use one of our rotational kinematics equations to solve for the final rotational velocity. If you go back, we could use this one. We're trying to solve for the final rotational velocity. The initial is 0. The rotational acceleration is 0.005. revolutions per second squared, and the time is 60 seconds. So the final rotational velocity is 0.3 revolutions per second. So in 1 second, it goes about a third of the way around. The second question is asking how many revolutions does the merry-go-round make in this time? So we're looking for how many revolutions. It's asking for the rotational distance that this thing spins through after 1 minute. So now we're looking for the rotational distance theta. And again, going back to my rotational kinematics equations, theta is equal to the initial rotational velocity times time plus 1/2 rotational acceleration times t squared. So I could use this one to solve for the rotational distance theta. The first term is 0 because the initial rotational velocity is 0. So I'm just left with the second term, 1/2 times the rotational acceleration times time, 60 seconds. And don't forget to square it. So 60 seconds squared multiplied by 1/2 multiplied by 0.005. 9. And what are our units? Well, I have seconds squared on the bottom and I have seconds squared on the top, so I'm left with 9 revolutions. Side note, if I wanted to convert revolutions to radians, I could say it's 9 revolutions. It's gone around 9 times. I can make the conversion that 1 revolution is 2 pi radians. And this will help me convert to radians because revolutions cancel out and I'm left with radians on the top. So I'm going to do 9 times 2 times pi. 56.5 radians in 1 minute. How many degrees is that? Well, let's do the same thing. How many degrees is in 9 revolutions? My conversion factor is 1 revolution is 360 degrees. So I do 9 multiplied by 360. 3,240 degrees. So these are all describing the rotational distance. How much of an angle has this thing rotated through in 1 minute? It's gone through 9 revolutions, or 56.5 radians, or 3,240 degrees. So we're simply applying kinematics equations to rotational motion now. Now you might be wondering, is there a relationship between the linear velocity and the rotational velocity? Linear velocity being, v, and rotational velocity, omega. If you take a look at this animation to the right, see the red dot and the blue dot. Notice that they both go around a complete circle in the same amount of time. Right? They go through one revolution in the same amount of time. They both go through 360 degrees in the same amount of time. That means that both of them have the same rotational velocity, omega. But one of them has a larger linear velocity, and that is the one on the outside. Why? Because in 1 second, this one on the outside travels a lot farther of a distance. Look, as these things go around one circle, the blue one travels a lot farther because the circle is bigger. The red one travels a lot shorter because its circle is smaller. So the further I get from the axis of rotation, the larger my linear velocity becomes. So it depends upon the radius, how far you are from the center, r. And it's a direct relationship. The linear velocity v is equal to the radius r multiplied by the rotational velocity omega. Now to use this equation, you have to make sure that omega is in radians per second. If it's in degrees, you'd be multiplying a radius multiplied by a degree. It doesn't really make sense. So you need to multiply it by something in terms of radians. So I have a question for you. Choose all the following statements that are correct. If an object has a rotational acceleration of 0, it must not be rotating. If an object has a rotational velocity of 0, sorry, I think I read that wrong. If an object has a rotational acceleration of 0, it must not be rotating. If an object has a rotational velocity of 0, it must not be rotating. If an object has a constant rotational acceleration, it must also have a constant rotational velocity. Pause the video, think about which ones you think are true, and when you're ready, press play. We'll go over it together. The correct answer here is that only the second one is true. The first one is false because if the object has a rotational acceleration of 0, that means alpha is 0. Does that necessarily mean that the object is not rotating? No, it could mean, what it does mean is that the rotational velocity is constant. It's not changing. It could be 0, or it could be constant, 10 RPM, right, and not changing. Could be a constant 20 RPM and not changing. But it doesn't necessarily mean that it's not rotating at all. The second one is true because if the rotational velocity is 0, that does mean that it's not rotating, right? It's simply stuck in place. It's just like saying linear velocity is 0, it's stopped. If rotational velocity is 0, it's also stopped. No motion. If an object has a constant rotational acceleration, it must also have a constant rotational velocity. That's not true. If it has a constant rotational acceleration, that means it's either speeding up in the circle or slowing down in the circle. So its rotational velocity is constantly changing. That's the case. Another question for you. Choose all the following statements that are correct. A child moves from the center of a merry-go-round to the edge of the merry-go-round. What happens? Does the angular velocity increase? Sometimes I say angular velocity, sometimes I say rotational velocity. It means the same thing. Does the rotational velocity increase? Does linear velocity increase? Or does angular velocity decrease or linear velocity decrease? Think about each of these statements, decide which ones you think are true for this situation, pause the video, and then come back when you're ready. The only statement is true here is that the linear velocity increases. Remember, as I go from the center out towards the edge, my radius is getting bigger, right? So the relationship between the linear velocity and the angular velocity is v equals r omega. So as r goes up, linear velocity also has to go up. But the merry-go-round's angular velocity is not changing, right? Whether I stand in the center or all the way out on the edge. So that doesn't change, but the linear velocity does go up. I'm going to stop here. This gives you a nice brief general overview of rotational kinematics. Next time, let's talk about the cause of why objects rotate in the first place. And if you remember from linear motion, the cause of linear motion was a force, right? I need a force to get something to start to move. I need a force to get something to slow down. With rotational motion, I need what's called a torque. So we're going to define torque next time, and we're going to see how that affects the motion of something that's rotating. I'll see you then. Bye.